Welcome back to this next video in which we are discussing prime ideals. Okay, so in this video what I want to discuss is what happens if you take a commutative ring and you quotient it out by a prime ideal. What do you end up with? Okay, so in previous videos in this playlist we've seen that if you quotient a commutative ring out by a maximum ideal, you end up with a field. What we're about to see is that if you quotient a commutative ring out by a prime ideal, you don't quite end up with a field, but you do end up with an integral domain. Okay, so let me show you this. So we're going to be asking what happens if you take your commutative ring and you quotient it out by a prime ideal. Okay, and my claim is that this is an integral domain, so I'll put that an integral domain. Okay, so I want to prove this, and I also want to prove it the other way round. So I want to prove that if you quotient a commutative ring out by an ideal and end up with an integral domain, then you can instantly conclude that that ideal was a prime ideal. And we're going to use that to show that all maximal ideals are prime ideals. Okay, so that's a overview of what we're going to discuss in this video then. Okay, so let's start proving it this way though. Let's start by proving that if you quotient out a commutative ring by a prime ideal, you end up with an integral domain. So let's draw a little picture to understand the quotient rings. We should now be familiar with how quotient rings work. Okay, so here is our commutative ring, and I'll just colour this in. So we'll have the entire commutative ring here that we start off with, coloured in pink here. Okay, and now let me mark on the prime ideal onto this. So let's say that this subset here, which I'll call P, is my prime ideal. Okay, now if I quotient out by my prime ideal, what I'll do is I will I'll partition up the commutative ring capital R into the additive cosets of my prime ideal. So it'll be broken up into these additive cosets. So in my picture I've just drawn 4, but of course usually you end up with far more than 4. Okay, so here are the additive cosets of my prime ideal capital P here, and these additive cosets are going to become the elements of my quotient ring, and then we can define an addition law on those cosets and a multiplication law on those cosets, which involves taking representatives from the cosets, adding or multiplying those together in the initial ring, getting the answer to that, and then taking as your coset answer the coset that contains the answer in the ring. Okay, and we know that that's well defined and that it indeed does actually obey the axioms of ring theory. Okay, and we know also that if we start off with a commutative ring, the quotient ring that we end up with will be a commutative ring. What I now want to show is that this is actually going to be an integral domain if we quotient out by a prime ideal. Okay, so remember, an integral domain is a non-zero commutative ring. Okay, so I do just need to argue as to why it won't be the zero ring. It won't be the zero ring because remember, the prime ideal is a proper ideal. Okay, so to get the zero ring you have to quotient a ring out by itself. Okay, so the unit ideal. So as long as you're quotienting out by a proper ideal, you will not end up with the zero ring. So it will be a non-zero commutative ring, and it also needs to obey that property that if you multiply together two non-additive identity elements together, okay, so the additive identity in this case is going to be the coset, which is the initial prime ideal, because this would of course contain the additive identity from the initial ring, so we could call this 0 bar. Okay, so I want to prove that if I take two cosets that are not equal to the additive identity, so let's say I take this one here, which we'll call A bar, so let's say it contains a representative A, which I've chosen to name this coset after, and let's take this coset here, which contains B, and I'll name this coset after B there, so we'll call it B bar. Okay, so I take two non-additive identity cosets in my quotient ring here, and I want to show that if I multiply together two non-additive identity cosets in my quotient ring, that I will not get the additive identity coset as my answer. Okay, you cannot multiply two non-additive identity cosets together in an integral domain and get the additive identity coset. That's the definition of an integral domain. Okay, so let's show this then, but using the fact that this is a prime ideal here. Okay, so if I multiply together the cosets A bar and B bar, which are my two arbitrary non-additive identity cosets then, how would I actually do this in my quotient ring? Well, of course, the way it works is that you reduce it down into multiplication in the initial commutative ring. So you take a representative from here, take a representative from here. We might as well take A and B. Of course, we've proven in the video on quotient rings that this is well defined, so it doesn't matter which representative you take. But since we've only come up with the representative A and B here, we might as well just take those. And we multiply them together in the initial commutative ring, so I'll colour that multiplication in pink here because it's in the initial ring, capital R here, and then we just take the coset that contains that. Now here's the point where we use the fact that this ideal is a prime ideal, because A times B, whatever the answer is here, it cannot be in the prime ideal. And why is that? Because we know that a prime ideal is one of these ideals where if you take two elements that are outside of the prime ideal and multiply them together, you cannot get an answer that is in the prime ideal, because the only way that you can multiply two things together and get something in the prime ideal is if one or both of them are multiples already, are in the prime ideal already. Okay, are already elements of the prime ideal. A and B were not elements of the prime ideal. Look, they're very evidently outside of the prime ideal. They were in cosets separate from the prime ideal here. Okay, so we're multiplying together two elements that are not in the prime ideal, and that must give us an answer that is not in the prime ideal. Okay, so maybe it's over here. Maybe A times B is in this final additive coset here. Okay, and therefore we will end up with a coset that is not equal to the additive identity coset in our quotient ring, and therefore I have indeed shown you that whenever you take two non-additive identity elements in the quotient ring and multiply them together, you will end up with another element that is not the additive identity in your quotient ring. Okay, so there we have proven forwards. We've proven that if you take a commutative ring and quotient it out by a prime ideal, you will get a quotient ring that is an integral domain. Excellent. Now let's prove it the other way around. So let's say we have taken a commutative ring and we've quotiented it out by some ideal, and the answer is an integral domain. Okay? What I now want to see is, can I conclude that my ideal was a prime ideal? Okay, so let's once again draw a fresh picture for this then. So I'll draw a nice fresh picture here. Okay, so we'll have our commutative ring once again represented in pink here. So I'll just outline it in pink as before. Okay, now what we've done again is we've got some ideal here, okay, which we don't yet know is a prime ideal. We want to prove that it's a prime ideal, but we know it's an ideal. Okay, so we can use it to quotient out the initial commutative ring, capital R, like so, and I think I might draw slightly more additive cosets this time. So here it's additive cosets, and the structure that we've ended up with, the quotient ring, where the elements are, of course, the cosets that we've partitioned our initial commutative ring up into, this quotient ring is an integral domain. So we are given the fact that if we multiply two non-additive identity cosets, so any of these cosets, so remember this one will be the additive identity coset here, so if we multiply together any of these cosets, the non-additive identity cosets, so I'll just circle these in yellow, if we multiply any of those two together, we end up with another coset that is not the additive identity. Okay, so that's excellent. And what we want to prove now is that the ideal here was a prime ideal. Now what do we need to prove in order to prove that it's a prime ideal? Well, actually all we need to prove is that if we take two elements that are not in the ideal and multiply them together, so take two elements, so for all A and B, which are elements of the ring, subtract the ideal, so all elements that are outside of the ideal in the ring. And what we need to show is that if you multiply these two together, that you also end up with something that's outside of the ideal. Okay, so that it's not an element of the ideal, it's back outside the ideal. Okay, and this is equivalent to showing us it's a prime ideal, because that's exactly what you do need to show. A prime ideal is one where the only way you can multiply two things together and get something that's in the ideal is if one or both of them are in the ideal already. Okay, so if we take two elements that are not in the ideal, it must be the case that the answer to their product is not in the ideal. So that's what we need to show here. Okay, so in the picture here, we're just taking an arbitrary little a here, and an arbitrary little b outside of the ideal, so clearly they're nicely outside of the ideal in my picture here. And of course, we're now trying to gain some insight into what the product of these two is. Okay, now the only thing we're given here is that the quotient ring is an integral domain, so we're somehow going to have to use that. Okay, so we're trying to gain insight into what a times b is equal to. So the way we're going to do it is we're going to say, okay, a must be in some coset in the quotient ring. Okay, so let's say it's in the coset a bar, named after itself. Okay, b must be in some coset in the quotient ring as well. Okay, and we'll call that coset b bar. And because a and b were both supposed to be outside of the ideal, it means that they're both in cosets that are not the additive identity coset. Okay, so I can conclude that a and b are not elements, so not elements, of the additive identity coset. Okay, now what I can do is use the fact that it's an integral domain, and what it being an integral domain tells me is that if I multiply these two cosets together, a bar and b bar together, in the quotient ring, so this is multiplication in the quotient ring, whatever the answer is, it is not the additive identity coset, so this is not equal to the additive identity coset. But how would I actually perform this multiplication? Well, of course, I take a representative from here and take a representative from here, and this is where I can reduce it into multiplying a and b together. So I'll take the representative a and I'll multiply it with the representative b, and then take the coset that contains that, and I'm now given that this cannot be the additive identity coset. So what that is effectively telling me is that a times b is not in the additive identity coset, i.e. it's not in the ideal. So phrasing this another way, AB is not an element of the ideal, okay, which is exactly what we've got here. That's exactly what we needed to prove. So I've now started with the condition that A and B were outside of the ideal, and I've arrived at this statement here that A and B, A times B rather, is not in the ideal. It's in the portion of the ring outside of the ideal. Okay, so from the fact that the quotient ring was an integral domain, you can therefore conclude that the ideal that you quotiented out by was a prime ideal in the ring. Okay, so it goes both ways then. If you take a commutative ring and quotient it out by a prime ideal, you end up with an integral domain. If you take a commutative ring, quotient it out by some ideal which you don't yet know is a prime ideal, and you get an integral domain as the answer, you can instantly conclude that that ideal was a prime ideal. Okay, so that's rather lovely. Okay, so the final thing then that I want to prove in this video is that all maximal ideals are prime ideals. So let's say we've got some maximal ideal, capital M here, which is an ideal of our commutative ring, capital R. So I'll just remind you of what the definition of a maximal ideal is. A maximal ideal is a proper ideal, just like a prime ideal, so it's not allowed to be the unit ideal, it's not allowed to equal the entire ring. Okay, and the other condition that is there for a maximal ideal is that there is no other proper ideal that completely contains the maximal ideal M, and it is itself completely contained in R, i.e. there does not exist another ideal such that M is completely contained within this other ideal, and this other ideal is completely contained within R, and that should be proper containment, so get rid of these lines. Okay, so I apologise for that, so I'll colour it in to hide my mistake here. So it should be properly contained. Okay, so M must be properly contained within I, and I must be properly contained in R. Okay, and I claim that there's no such ideals that satisfy that. You can't find a bigger proper ideal that contains all of M and is still a proper ideal in R. Of course, you can find another ideal. It would be the entire ring, capital R. That's an ideal, but that's not a proper ideal. Okay, so it's maximal with respect to proper ideals, basically, in the ring, capital R. Okay, now, in the video on maximal ideals, we showed that if you quotient out a commutative ring by a maximal ideal, you end up with a field. Okay, so this will be a field. And we did that using the correspondence theorem, or the third isomorphism theorem for quotient rings, which states that there is a correspondence between the ideals that properly contain the ideal that you're quotienting out by, and which are in between that ideal and the entire ring. and the ideals in the quotient ring. Okay, so if there's no ideals that are in between the maximal ideal and the entire ring, then it means that there's only two ideals in the quotient ring, which are the zero and unit ideals. Okay, and that's equivalent to showing that it's a field. Okay, now I claim that this now allows us to conclude that M is a prime ideal. Okay, so I claim that all maximal ideals are going to be prime ideals. So not only is it a maximal ideal, it will instantly, the instant it is a maximal ideal, it will also be classifiable as a prime ideal. Now, why is that the case? Well, because all fields are integral domains. Okay, an integral domain, remember, is a commutative ring that is not the zero ring, which then has the case that where it's the case that if you multiply together two non-additive identity elements, you get a non-additive identity element. A field is a non-zero commutative ring in which all elements have multiplicative inverses, and it's very easy to show, and we have shown in previous videos, that if you have multiplicative inverses for all non-additive identity elements, that you can then conclude that if you multiply together two non-additive identity elements, you must get a non-additive identity element. So because all fields are integral domains, it's not the case that all integral domains are fields. For instance, the integers is an integral domain, but it's not a field, but it does go this way. All fields are integral domains, okay? You can then conclude that you've quotiented out R by this ideal here and got an integral domain, and now we've shown that if you do quotient out a ring by an ideal and get an integral domain, that you can conclude that that ideal was a prime ideal. So we can just apply that now here, and then we can conclude that that maximal ideal was a prime ideal. Okay, so all maximal ideals then are prime ideals. It doesn't work the other way around though, that all prime ideals are maximal ideals. Okay, it works this way round, that if you're a maximal ideal, you're also a prime ideal. It doesn't work that way round, that if you're a prime ideal, you're a maximal ideal. Okay, and with that, we will end this video on prime ideals.